Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is switches. Our objective today is to take a close look at a simple electromechanical device known as the switch. We'll discuss their purpose and observable electrical characteristics in the open and closed position. Additionally, we'll discuss important switch terminology, including the difference between normally open and normally closed switches, and the difference between momentary and maintained contacts. Finally, since the topic is incredibly relevant to switches, we'll discuss shorts and opens inside basic series circuits. This lecture is meant to be a continuation of the basic series circuit properties lectures, and as such we'll be making use of this previously discussed content. If you haven't watched these lectures yet, or perhaps only dimly recall its contents, by all means take the time to do so now. Those skills developed in the Kirchhoff's voltage law and the voltage divider rule lectures will be employed during the course of this lecture. Today we'll discuss the simple electromechanical device known as the switch. As we'll soon learn, switches come in many forms and perform many functions, the most obvious being the selective enabling or disabling of electrical loads placed in series with a switch. You might have 99 problems, but the switch shouldn't be one. As simple as the switch seems, an instinctive understanding of this device is essential for any progression in later more advanced topics including motor control and digital electronics. The physical arrangement of switches govern the physical behavior of systems, and logical operations of immense complexity can be developed using switches that can be placed in one of two mutually exclusive binary states, opened or closed. At risk of blowing your mind, I'll introduce two basic logic operators, the AND function and the OR function, before we close out this lecture. At its most basic level, it should come to you as no surprise that an open switch will not allow current flow and that a closed switch will allow current to flow. An open switch is idealized as an infinite resistance through which no current can flow. A closed switch is idealized as a 0 ohm resistance, or short, through which current can flow. Given our understanding of the most fundamental of series circuit properties, that current in a series path is the same anywhere in that path, a switch in series with an electrical device is an incredibly important application of this principle. If there exists no current flow through a device in a series relationship, there exists no current flow through the whole series relationship. Switches and circuit protection devices like fuses and circuit breakers placed in series with an electrical load selectively enable or disable operation of the entire series path, because current in a series path is the same anywhere in that path. An open switch does not allow current to flow to the electrical load. A closed switch does allow current to flow to the electrical load. Recall that voltage drop across resistors in a series relationship is proportional to both resistance and current via Ohm's law. V equals I times R. Since resistors in a series relationship carry the same current, it can be stated that the voltage drop will be directly proportional to resistance. The smallest resistor in a series relationship will have the smallest voltage drop. The largest resistor in a series relationship will have the largest voltage drop. Given a closed switch is idealized as a 0 ohm resistive path, it can be stated that no voltage will be dropped across the switch when it's closed. Additionally, given an open switch is idealized as an infinite resistance, and you can't get much larger than infinite, this presents the largest resistance in the series path, and all voltage will be dropped across an open switch. These facts bear repetition since they are essential to understanding observed electrical characteristics of closed and open switches. A closed switch will allow current to flow. An ideal closed switch, being a 0 ohm resistor, will have no voltage dropped across its two terminals. Although in practice a real closed switch does present a measurably small amount of resistance and therefore might experience a tiny voltage drop. An ideal open switch, being an infinite resistance, will not allow current to flow. Depending on its position in the circuit, a point I'll come back to clarify, an open switch will have voltage drop across it. For the case of a single switch in series with an electrical load, all voltage will be dropped across the switch when the switch is open. For the case of a closed switch in series with an electrical load, all voltage will be dropped across the electrical load. Pause to contemplate the physical construction of a switch and the numerous environments it might be employed. Obviously, a switch must be built strong enough to handle the current through it and the voltage across it. You can't expect a tiny dip switch used on a protoboard to make or break the current to a large industrial motor, and the use of sulfur hexafluoride switchgear ordinarily reserved for a large hydroelectric dam might be a bit of an overkill. The point is, the mechanical aspect of making or breaking a conductive path is a brief moment in time when the non-ideal nature of switches and real-world physics become vitally important considerations. The business end of a switch are the contacts. These are electrically conductive devices that, when touching, allow current to flow, and when separated, do not. They're physical parts, and when subjected to abuse or long use, can wear out and fail. Making a connection is the act of closing a switch. Breaking a connection is the act of opening a switch. Recall from the resistance lecture, even air can be considered a conductor between two high voltage points in close proximity. A high power switch must not only be physically larger to accommodate for this possibility, also when breaking a connection, it must rapidly and forcefully rip the moving contacts apart to prevent the electrical arc that forms between the contacts from continuing. As we'll learn in the circuit protection devices lecture, sometimes pretty exotic methods are used to extinguish this arc. Additionally, the act of making the connection must occur as rapidly as possible, but this rapidity brings with it the possibility of switch chatter or bounce. Imagine parking your car at 60 miles per hour. Chances are cars on either side of you, in the front and back, might show signs of mechanical wear. We'll learn in later lectures that physically moving contacts can be replaced by power electronics devices with no moving parts, such as a solid-state relay for high-speed switching applications. Realize that a switch selectively enabling or disabling an electrical load can be on either side of the electrical load and the source. Recall that a circuit is exactly as the name implies: a circuit, a loop, or a closed path with return to the supply. One could place a switch between the positive terminal of the source and the electrical load. This is known as high-side switching. Sometimes it's called sourcing because the switch connects or disconnects the source to the electrical load. In a high-side switching arrangement, when open, the switch experiences all the voltage drop. Both terminals of the electrical load are at low potential, and there is no voltage differential across it. The electrical load is de-energized when the high-side switch is open. When the high-side switch closes, both terminals of the switch are at the same high potential. However, there is no voltage differential across it. The electrical load experiences all the voltage drop. The electrical load is energized and experiences flowing current. Equally as effective, one can place a switch between the electrical load and the negative terminal of the source, effectively eliminating the return path for current. This is known as low-side switching, or alternately, sinking. In a sinking or low-side switching arrangement, a connection to the source always exists, and the low-side switch simply connects or disconnects the return path. I like to think of a sinking connection as a sink full of water. The connection to the source always exists, and the sink is always full of water. The only thing preventing the electrical load from operating is flowing current. Closing the low-side switch is like pulling the plug from the bottom of a sink. In a low-side switching arrangement, when open, the switch experiences all the voltage drop. Both terminals of the electrical load are at high potential. However, there is no voltage differential across it, and current will not flow. The electrical load is de-energized. When the low-side switch closes, both terminals of the switch are at the same low potential, and there is no voltage differential across the switch. The electrical load experiences all the voltage drop. The electrical load is energized, and current can flow. Conceptually, a high-side and low-side switch do the exact same thing, though in practice, you'll most often see high-side switching arrangements because of their inherent safety characteristics, due to customary grounding of the negative terminal. When the negative terminal of a source is intentionally connected to ground, there exists the possibility that an electrical load and a low-side switching arrangement can unexpectedly energize without closing the switch. Allow me to demonstrate. Consider the high-side switching arrangement. It is a series relationship of a source with an intentionally grounded negative terminal. A fuse, that's what that little squiggly S is in our schematic. A high side switch and an electrical load. The fuse, as we'll soon learn in the circuit protection lecture, is a device that simply melts when too much current flows through it. In this case, one side of the electrical load is always connected to ground. As previously discussed, an operator starts the machine by closing the switch and connecting to the source, and stops it by opening the switch and disconnecting the source. Consider what would happen if an errant piece of conductive wire accidentally bridged the electrical load and something connected to ground at its bottom terminal. In this case, a whole lot of nothing would happen because that side of the electrical load is already touching ground via the intentionally grounded negative terminal on the source. The ground reference can be considered not a single point, but a large pool at the same potential. The operator can still start and stop the machine by closing and opening the switch. Though as we'll soon learn in the circuit protection lecture, current would be traveling through an unintended ground path, and this leakage current could be detected and resolved with a ground fault current interrupter, a GFCI. Consider a different location of the errant wire where it touched the top terminal of the electrical load. If the switch is open, nothing would happen. The electrical load experiences ground potential on either side of it, and there is no voltage differential across it. The electrical load would not energize. However, if an operator closed the switch, the source no longer sees just the electrical load, but rather the electrical load in parallel with essentially a 0 ohm conductive path. This is a short, and a short presents no resistance to the source, and current will rise to great magnitudes. The fuse, being a circuit protection element in series with a switch and the electrical load, also experiences this same current and simply melts, becoming an open circuit through which no current can flow. In this case, all voltage would be dropped across this new open, this being the two terminals of the vaporized fuse. The presence of an intentionally grounded source and a fuse in series with the load allowed for the detection and resolution of the short in a high side switching arrangement. At no time did the electrical load unexpectedly energize. Now consider the exact same scenario for a low side switching arrangement. Consider what would happen if an errant piece of conductive wire accidentally bridged the electrical load and something connected to ground at this bottom terminal. In this case, the electrical load could unexpectedly energize. And here's what's scary: without the operator closing the switch. The switch is essentially bypassed by this errant wire connected to ground. Because of the pooled ground arrangement, there exists a return path to the source. In this case, the fuse cannot detect or resolve this accidental short because current drawn by the electrical load is inside its operational range. An errant short inside low side switching arrangements can sometimes unexpectedly energize the electrical load, often with horrible consequences. At all times, you need to ensure that all forms of hazardous energy have been blocked, released, locked, and tagged out, and that none can build up during the course of your work. Know where the emergency off switch is and have access to it at all times. I would be negligent in my duties as an instructor if this lecture did not include a tedious illustrated example problem. Not to worry though, because this should be pretty easy stuff by now, and I'll spice this example up by including a switch, quick discussion of nodal voltages, and introduce some faults like short circuits and opens. Consider this circuit consisting of a 20-volt source with a grounded negative terminal in series with R1, a 200 ohm resistor, R2, a 300 ohm resistor, a switch I'll call SW1, and R3, a 500 ohm resistor. Notice that I've labeled the nodes A, B, C, D, and E. Pause the lecture and consider the voltage drop across each component and the current through each component, including the switch, for two scenarios: when SW1 is open, and again when SW1 is closed. Here's how I'm going to solve for the desired unknowns. You may have used different steps in a different order, but ultimately our answers should agree. The first scenario is astoundingly easy. When SW1 is open, no current can flow through any element. With no current flowing through the circuit, there will be no voltage dropped across the resistive elements in this circuit. That being said, since there is a voltage rise, there must be a voltage drop. The voltage drop will occur across the open switch. V1, V2, and V3 all equal 0 volts. VSW1 equals 20 volts. Consider what this means at the nodal level. If there is a 20 volt drop across the switch, there's a 20 volt differential between node C and D. Since there is no differential across R1 or R2, this means node A, B, and C are all at 20 volts with reference to the grounded negative terminal. Since there is no differential across R3, this means that node D and E are both at 0 volts with reference to the grounded negative terminal. It makes sense. Using double subscript notation, VAB is 0 volts, VBC is 0 volts, VCD is 20 volts, and VDE is 0 volts. If we wanted to use a common reference like ground, we could also say that VAE is 20 volts, VBE is 20 volts, VCE is 20 volts, and VDE is 0 volts. Using single subscript notation, where node E at ground is an agreed upon common reference, we can say VA, VB, and VC equal 20 volts, and VD equals 0 volts. If this seems like one of those glass half empty or is the glass half full style questions, it kind of is. The point is that voltage is a 2-point measurement, and you have to be clear which 2 points you're talking about. Now let's consider what happens when the switch is closed. This second scenario is equally as easy as the first if you have an understanding of basic series circuit properties. We can use the voltage divider rule to solve for V3. You heard me right, I'm going to solve for V3 first, not V1. Why? Because I'm crazy, and I like being crazy and unpredictable. Actually, I'm doing this to prove a point that you can solve for desired quantities using different methods in a different order and still get the same results. Substituting in the necessary values, where the closed switch SW1 presents a 0 ohm resistive path, we find V3 to be 10 volts. Using Ohm's law, we can solve for the current through R3, where I3 is equal to V3 divided by R3. Substituting in the necessary values, we find I3 to be 20 milliamperes. Using the most fundamental of series circuit properties, that current through elements hooked in series is the same, we can say, no calculations required, that the current through every single element in this circuit is 20 milliamperes. I1 equals I2 equals ISW1 equals I3, and they all equal 20 milliamperes. Using another statement of Ohm's law, we could solve for the voltage drop across R1, where V1 equals I1 times R1. Substituting in the necessary values, we find V1 equals 4 volts. To prove a point, we can use Ohm's law to solve for the voltage drop across the closed 0 ohm switch 1, where VSW1 equals the current through it times its resistance in the closed state. Substituting in the necessary values, we find the voltage drop across the closed switch equals 0 volts as anticipated. We can now use Kirchhoff's voltage law to solve for the remaining voltage drop V2. Kirchhoff's voltage law analysis of this series circuit suggests that our rise E equals the summation of our drops V1 plus V2 plus VSW1 plus V3. Substituting in the given value of our source and the calculated values of V3, V1, and VSW1, we can solve for V2, where V2 is found to be 6 volts. Again, consider what this means at the nodal level. If there is a 4 volt differential across R1, using double subscript notation, we can say that VAB equals 4 volts. If there is a 6 volt differential across R2, it can be said that VBC equals 6 volts. If there's a 0 volt differential across our switch, it can be said that VCD equals 0 volts. And if there's a 10 volt differential across V3, it can be said that VDE equals 10 volts. Now again, consider these nodal voltages using common frame of reference. If the source provides a rise of 20 volts between node A and E, and R1 drops 4 volts from A to B, it can be said that node B is only 16 volts higher than node E. Therefore, VBE equals 16 volts. Given R2 drops 6 volts from B to C, This means node C is only 16 minus 6, or 10 volts higher than node E. Therefore, VCE equals 10 volts. Since there's no voltage drop across the closed 0 ohm switch from C to D, D can also be considered 10 volts higher than our agreed upon reference at E. It makes sense. For the closed switch condition using single subscript notation, where node E is an agreed upon reference point at ground potential, it can be said that VA equals 20 volts, VB equals 16 volts, and both VC and VD equal 10 volts. Again, if this seems like one of those other side of the looking glass scenarios, it kind of is. The point is, again, that voltage is a 2-point measurement, and you have to be clear which 2 points you're talking about. Although the voltage on one side of this switch is 10 volts above ground, the voltage on the other side of the switch is also 10 volts above ground. There is no differential between them, and the voltage differential across the closed switch is 0 volts. Let's talk about shorts and opens inside series circuits using the illustrated example problem with a closed switch as a basis of comparison. Before doing so, I want you to solve for power dissipation of each component during unfaulted conditions. We'll use these figures in a moment to make an important point about power dissipation with a short in our circuit. P1 equals V1 times I1, P2 equals V2 squared divided by R2, PSW1 equals VSW1 times ISW1, P3 equals I3 squared times R3. Substituting in the necessary values, we find P1 equals 80 milliwatts, P2 equals 120 milliwatts, and P3 equals 200 milliwatts. Notice the power dissipated by the switch is 0 milliwatts because we are assuming no voltage drop across it. Let's put these figures in our pocket and move on with our discussion of shorted components. A short is the errant addition of a low resistance path in parallel to a component. The parallel combination of anything, in effect a 0 ohm resistor, effectively yields 0 ohms of resistance for the shorted component. The shorted component, and the shorted component only, is removed from consideration. If we were to short out R3, the 500 ohm resistor, with a 0 ohm path from node D to E, pause the lecture and consider the anticipated effects. Notably, how will the shorting of R3 affect total resistance? How will total resistance affect source current? And how will source current affect the voltage drop across the remaining elements in this series combination? And finally, how will this affect the voltage drop across R3? You don't even need to worry about specifics nor busy yourself with calculations just yet. Just answer these simple questions with simple answers. Will the desired quantity go up, go down, or stay the same? Use your understanding of Ohm's law to predict how this circuit will respond with R3 removed from consideration. If R3 is removed from consideration by becoming in effect a 0 ohm resistor, the total resistance of our series combination is now just that of R1 plus R2. Total resistance has gone down. With reduced total resistance, current will go up. With increased current draw, the voltage drop across R1 and R2 will increase. The voltage drop across the closed switch would still be 0 volts. I'll kind of neglect the closed switch for the rest of this problem, since that's really the purpose of a closed switch. It enables current flow, but otherwise in no way influences circuit analysis. Current ordinarily intended for R3 is routed through the 0 ohm short instead. With no current flowing through the shorted R3, there should be no voltage drop across this shorted component. Using Kirchhoff's voltage law on our in effect 2 resistor series circuit, it can be additionally stated that V1 and V2, now being the only voltage drops in this circuit, all voltage rise will be dropped across these 2 remaining components. E equals V1 plus V2. It's like the shorted R3 isn't even there anymore. This could be a potentially dangerous situation if R3 was an essential current controlling element, keeping current below a manageable limit. Additionally, with a shorted R3, we've effectively created a low side switching arrangement. Finally, with increased current draw and voltage drop by R1 and R2, the power dissipated by these remaining resistive elements sharply increases. Now that we've briefly discussed the expected results of a shorted component in sufficiently general terms, just put some numbers in there. pause the lecture and see if you can determine the anticipated current draw, the voltage drop across each component, and the power dissipated by each component when R3 is shorted out and effectively removed from consideration. When R3 is no longer in our circuit, the only opposition to current remaining is that posed by R1 and R2. Total resistance drops to 500 ohms. With reduced total resistance, source current should rise. We should expect approximately 40 milliamperes of current flowing through this circuit with a shorted R3. Double the current because our resistance dropped in half. Given power is a geometric function of current, start thinking now of how hot these remaining resistors are getting. With increased current draw through our remaining resistors, we should expect a larger voltage drop across them. V1 equals 8 volts, V2 equals 12 volts. With current being diverted through the short circuit, no current should flow through R3 and no voltage drop will occur across it. Notice that V1 at 8 volts plus V2 at 12 volts is equal to our total voltage rise of 20 volts. Again, providing additional proof that no voltage drop will occur across our switch nor our shorted component. Finally, with increased current draw and an increased voltage drop across R1 and R2, consider the power dissipated by these two remaining components. P1, the power dissipated by R1, rises dramatically from 80 milliwatts to 320 milliwatts. For P2, the power dissipated by R2, again, the power rises dramatically from 120 milliwatts to 480 milliwatts. Notice the dramatic leap in power dissipation because of power's geometric relationship with current. This goes to show you that shorting out one component inside a series relationship can cause others to go up in smoke. The takeaway points about this discussion on shorted components is this: the shorted component is removed from consideration. With decreased total resistance, current increases. With increased current, voltage drop across remaining components increases. No current flows through the shorted component, but is rather diverted through the short. With no current flowing through the shorted component, there is no voltage drop across the shorted component. If you are presented a troubleshooting scenario in which an element inside a series relationship does not exhibit a voltage drop, and the other elements in a series relationship exhibit larger voltage drops than expected, that element with no voltage drop across it is the shorted element. The take-home point is this: know what to expect. Do the calculations first and have a basic understanding of how the system is intended to operate before you troubleshoot it. In addition to a low resistance wire placed in parallel, other equally heinous actions can effectively short out components. Consider a resistor incorrectly placed in a protoboard with both terminals connected to the same set of interconnected points defining a node. What if the switch was accidentally wired not in series as intended, but rather in parallel with R3? If the switch was open, 20 milliamperes of current would still flow through the circuit. If you close the switch, current would spike to 40 milliamperes because you're shorting out R3. I suppose you could do this if you wanted to, but that's not normally the intended purpose of a switch. They're normally used to stop or start current flow. Additionally, consider an ammeter placed not in series with these elements as required, but rather in parallel with R3. An ammeter can be modeled as an extremely low resistance path. This low resistance path in parallel to R3 effectively removes it from consideration, and the only elements controlling current are R1 and R2. Current again would spike to 40 milliamperes and not the 20 milliamperes anticipated for this series combination of three elements. Long story short, if current is too high, it's because resistance is too low. Either using the wrong components, you're building the wrong circuit, or you're shorting out components with a low resistance path, be it an errant wire, incorrect placement of a switch, incorrect use of an ammeter, or incorrect placement in the protoboard. Shorted components cause current to rise. If this was a current limited power supply, and we dropped the resistance too low, we might enter constant current mode where the power supply simply refuses to supply current in excess of some preset maximum by dropping its output voltage. If this source was protected by a circuit breaker or fuse in series with this circuit, and the shorted component caused current draw in excess of the breaker's or the fuse's rated current, the breaker would open or the fuse would pop, effectively turning off the whole circuit and preventing potential damage. A short, an event ordinarily associated with large current draw, precipitated an open, an event normally associated with no current draw. In this spirit, let us transition to the second common troubleshooting scenario: opens. An open is an infinite resistance through which no current can flow. Given our earlier discussion of open switches, the rest of this should be a cakewalk. With no current flowing through our circuit, no voltage drop will occur across any element. This being said, since there is a voltage rise, there will be a voltage drop somewhere within the circuit. The voltage drop appears across the open. Consider an open at node B, which necessitates the introduction of another node I'll call B'. No current flows through the circuit despite the fact that the switch is closed. All voltage will be dropped across these two nodes, B and B', basically the bottom of R1 and the top of R2. Ordinarily, these two terminals are hooked to the same node B, and it would be cause for concern to observe a 20-volt differential between them. Consider the difference between nodal voltages of this faulted circuit and our normally functional circuit employing a common reference. Ordinarily, we'd expect both the bottom of R1 and the top of R2 to be at 16 volts with reference to ground. However, with an open between the bottom of R1 and the top of R2, the bottom of R1 is 20 volts higher than our ground reference, and the top of R2 is 0 volts higher than our ground reference. The point is, there's a difference between our observations and expectations, and your knowledge of basic series properties can quickly pinpoint the nature and location of this fault. Between two components ordinarily connected to the same node, there is a voltage differential. You found the problem. This is the open circuit, and no current will flow through it. Beyond the systematic inspection of a series path using a voltmeter, an incredibly handy bit of advice in resolving open circuits is to just look at the circuit. Close inspection will often yield an off by one error, a severed wire, or a wire just dangling off in space. Take necessary safety precautions when troubleshooting such open circuits, lest you become part of the circuit. Before we close out our discussion of open circuits, consider this subtle modification to this faulted circuit and the host of complexities it brings with it. What happens when you open the switch? To rephrase this ever so slightly, what happens if there is more than one open in our series circuit? Here's a hint. All voltage will be dropped across the open. The only tricky part to this problem is this. Where is the open? The open is now between node B, the bottom of R1, and node D, the downstream side of our switch. All voltage is dropped between these two nodes, and like it or not, any voltage reading employing any of the points between B and D is absolute nonsense. B' and C, basically all of R2 and half of the switch, are in effect floating around in open space and in absolutely no way electrically connected to our circuit. What is the voltage differential between node B and your reference lead waving around in the air? How much higher potential does free space have than node D? The answer in both cases is a resolute I don't know, because it don't make sense. Realize this is a sticky, stinky, tangled mess that you do not want to F with under any circumstances. We've got a long way to go and a short time to get there, and any further discussion of this topic will only get us both sticky and stinky and the resolution no more untangled than it is now. It don't make sense. All voltages dropped across the open now being the two extremes of those elements in our formerly complete circuit still touching. Those elements floating in free space are electrically isolated from our circuit, and for all intents and purposes, could be in a different room, in a different county, in a different country, on a different planet. Any measurement employing any of these electrically isolated points have as much value as the currency from that alien planet. It don't make sense. All voltage is dropped across the open now being node B to D. As complicated as I may have made this subject seem, switches in series are routinely employed to perform one of the most basic logical functions, the logical AND. Consider two switches in series with one another, switch A and switch B, and an electrical load, perhaps a solenoid controlling a hydraulic press. The only way an operator can operate the hydraulic press is if they close both switch A and switch B simultaneously. If neither switch is closed, the press obviously won't operate because the solenoid obviously can't receive current via the two opens in its path. If an operator closes switch A but leaves switch B open, the solenoid still can't receive current via the open presented by switch B in its path. Conversely, if an operator closes switch B but leaves switch A open, the solenoid still can't receive current via the open presented by switch A in its path. Only when an operator reaches up with both hands out of the impact zone and closes both A and B simultaneously will the hydraulic press operate, because there is now an unbroken path to the solenoid controlling the valve. That's the point. Switches in series act as a safety chain. Both conditions A and B have to be met for the electrical load to energize. For this application, an operator has to have both hands off the press in a safe spot for the press to operate. Keep in mind, this needn't be limited to just two inputs. Any number of conditions can be placed in series, and they must all be met for a system to operate. All systems must be go before liftoff. If any single system isn't a go, there is no liftoff. The logical AND function is the most restrictive of logical functions. All input requirements must be satisfied for there to be an active output. Consider the opposite scenario, in which two switches are not placed in series with one another, but rather in parallel with each other. However, this parallel combination of switches is placed in series with an electrical load, in this case a lamp. This is the logical OR operator, and is the most permissive of logical operators. The logical OR operator will deliver an active output if any input is satisfied. If both switch A and switch B are left open, the electrical load won't operate. If switch A is closed and switch B remains open, the electrical load will operate. If switch A remains open and switch B is closed, the electrical load will operate. If both switch A and switch B are closed, the electrical load will operate. The closure of any switch in an OR relationship will deliver an active output. An application for such a function might be a lamp you wish to operate from either side of an impenetrable wall. Either switch A or switch B, or both together, will operate the lamp. Consider the subtle differences in phrasing between the AND and the OR operator. All versus any. They're both three-letter words that start with the letter A, but have totally different meanings, and confusing the two is unforgivable. We'll return to this topic in later lectures on motor control and digital logic. Functions of immense complexity can be built from simple operators like switches in series and in parallel with one another. Moving on, let's bring this lecture to a close with a brief examination of switch characteristics and the numerous varieties of switches. For those with only a cursory knowledge of bears, a first visit to the zoo might seem overwhelming. Not only are there grizzly bears, black bears, and polar bears, there are also panda bears, koala bears, sloth bears, spectacled bears, bear cats, teddy bears, and care bears. They're all furry quadrupeds that do the same thing in the woods. My point is that when I present you with this dizzying array of switch species, find some commonality between them, and from there determine the difference. The commonality for all switches is that there is a closed position and an open position. They all do the same thing. They allow or disallow current to flow through them. Among the terms we'll use to discuss switches are poles, throws, electrical isolation, actuation, activated versus deactivated, energized versus de-energized, normally open versus normally closed, mechanical interlock, and finally momentary versus maintained. Consider a collection of single-pole, single-throw switches known as DIP switches. DIP stands for Dual Inline Package. DIP switches have dimensions that allow them to be used on a prototyping board. Obviously, packages of DIP switches are not meant for high-power applications, but rather switching low-power signals. This schematic represents 10 single-pole, single throw switches. They're electrically isolated from one another. Electrical isolation means there is no electrical connection between switch 0 and switch 1 or any other combination of any other switches. Switch 0 could be sourcing 5 volts to one input. Switch 1 could be sinking 0 volts to another input. Switch 2 could be open, and switch 3 could be closed. It doesn't matter because they are electrically isolated from each other, meaning there is no electrical connection between switches. They're just housed in the same physical package. Now let's dissect the term SPST, single pole, single throw. A pole is the moving portion of a switch. A throw is the number of different connections the pole can make. An individual single pole, single throw switch has a single moving contact, hence the term single pole. Each pole has a single connection it can make, hence the term single throw. Again, an important fact about this 10-switch package is that each switch is not only electrically isolated from each other, they're all capable of being opened and closed independently of each other. Each single pole, single throw switch is an independent and isolated entity in no way, shape, or form connected to any other switch. The DIP package is exactly that, a package. It just holds them together. Don't confuse the package with an individual switch. Each individual switch can be considered independent entities. Each switch has a single pole, and each switch has a single throw. Here is an ohm meter being used to check the connectivity of switch 0. This switch is open, and the resistance across it is over the limit measured by the ohm meter. When I close the switch, resistance drops to an incredibly low value. This is one of the nonlinearities I spoke of earlier. If this switch carried a lot of current, there might be a measurable voltage drop across it. Consider a single pole double throw switch. This switch also has a single pole. However, this single pole can be placed in 2 different positions, A or C, hence the term double throw. This SPDT switch has a central common terminal I'll call B. The top terminal of this switch I'll call A. The bottom terminal of this switch I'll call C. The central terminal B is not electrically isolated from the A and C terminals, but rather serves as the common terminal for both A and C. Here's the ohm meter being used to test an SPDT switch. The central orange wire is the common B terminal. The purple wire on the left is the A terminal. The brown wire on the right is the C terminal. When the switch is in the down position, the ohm meter indicates there is a connection from B to A. This portion of the switch is closed. When I keep the switch in the same position and check connectivity between B and C terminals, the ohm meter indicates no connection. This portion of the switch is open. It makes sense. A single pole double throw switch is toggling between 2 different throws. When one is closed, the other is open, and vice versa. When I actuate or flip the connection to the up position, the single pole flops to the other throw. The ohm meter now indicates B and C are connected. This portion of the switch is now closed. If we go back to check the connection between the A and B terminals, the ohm meter now indicates no connection. This portion of the switch is now open. Again, it makes sense. A single pole double throw switch is toggling between 2 different throws. When one is open, the other is closed, and vice versa. This type of switch could perhaps be used to our advantage to control a device. For example, consider a light that can shine with 2 intensity levels. In the A position, the source sees R1 and R2 in series with the light. When the switch is toggled to the C position, the source only sees R2 in series with the light. With less resistance, current will increase and the intensity of the light increases. Another application of a single pole double throw switch might be to stop one device at the same time you start another. In the A position, only device A is energized. If the switch is toggled to the C position, device A is de-energized and device C is energized. A switch with a double throw is sometimes called a transfer or a changeover switch. For the obvious reason, it is transferring or changing from one connection to another. Consider a subtle modification to the single-pole double-throw switch by including a stable center state in which no connection is made to the outside world. This is now a single-pole triple-throw switch, sometimes called an SPTT-CO, where CO stands for center off. Sometimes the initial for triple is replaced with the number 3, so a single-pole triple-throw with the center off might be initialized SP3TCO, where again CO stands for center off. Consider a double-pole single-throw switch. This is like two single-pole single-throw independent switches ganged together. The only difference being these two poles close or open simultaneously with a single action. Each pole only has one connection it can make, hence the name single throw. Although mechanically linked, that's what this dotted line is supposed to represent. The two terminals of the top switch are still electrically isolated from the two terminals of the bottom switch. An application for this type of switch might be the desire to start or stop two devices simultaneously. Consider a double-pole double-throw switch. This device has two poles that can be placed in one of two positions. This is almost like two ganged single-pole double-throw switches mechanically linked together with a single action. The top single-pole double-throw switch is electrically isolated from the bottom single-pole double-throw switch. However, the B terminal on the left is now the common terminal, servicing both the A and C terminals on the right for the associated switch. Consider a triple-pole single-throw switch. There are 3 poles, and each pole can be placed into a single position. This is like 3 SPST independent switches ganged together. The only difference being that these 3 poles close or open simultaneously with a single action. Although mechanically linked, that's what this dotted line is supposed to represent. Each switch is still electrically isolated from every other switch. An application for this type of switch might be a contactor, a device commonly used to start or stop a device using 3-phase AC, something we'll learn about much later. If you're sensing a pattern developing, you're not the only one, because I could go on all day like this. Here's the key to the pattern, and use this key to guide your studies. Poles are the number of moving contacts controlled by one action. Single-pole devices like the single-pole single-throw, single-pole double-throw, and the single-pole triple-throw with center off have one moving contact. Double-pole devices like the double-pole single-throw and the double-pole double-throw switches have 2 moving contacts. Triple-pole devices like the triple-pole single-throw switch have 3 moving contacts. Throws are the number of positions each pole can connect with. Single-throw devices like the single-pole single-throw, double-pole single-throw, and triple-pole single-throw switch have only 1 throw each contact. Double-pole devices like the single-pole double-throw and double-pole double-throw switch have 2 mutually exclusive connections for each pole. Triple-throw devices like the single-pole triple-throw center-off switch have 3 positions each pole can connect to. If these definitions sound confusing, they really aren't. They're consistent and understandable. It just takes a lot of exposure time. Honestly, this is simple stuff because there's no trickery, theory, or math involved. It just takes some good old-fashioned head banging and staring at these pictures to make it stick. Luckily, you get lots of practice with this in later lectures on motor controls, so don't think this is the last time you'll see this material. For those seriously interested in this subject, be warned, switches are endlessly fascinating. In the interest of expediency, I've left out a number of numerous pertinent details I hope to return to one of these days when we delve deeper into these seemingly simple electromechanical devices with astoundingly powerful applications. Moving on, let's discuss 3 important distinctions between switches: that of their actuation method, natural deactivated state, and activation period. Actuation method is generally divided between manual and automatic means. A manually actuated switch might be a button, a lever, or a handle. basically something you hit with your hands or maybe your feet if you're sufficiently dexterous. A stop, start, go fast, lift off, or self-destruct button might be examples of manually actuated switches. An automatic switch might be a limit switch, something I'll show you in a little bit, a temperature switch, or a pressure switch, or any switch that doesn't require the presence of human hands or feet to hit. Such automated devices allow continuous function without constant human input or attention. Deactivated state is the most important of switch characteristics and governs how switches function when deployed in a circuit. Notice the careful use of terminology I've employed during this lecture. At no time have I said on or off, but rather limited myself to saying closed or open. Let's clarify this terminology up front and establish some limits and expectations. Previously, I used the terms make and break. Make means the act of closing an electrical connection. Break means the act of opening an electrical connection. I'm using the term actuation to mean the act of hitting, punching, poking, flipping, twisting, or otherwise diddling or dorking with a switch. An actuated switch can do one of two things. It can make or break a contact, i.e. a switch can close or open. This implies an important fact. The switch, prior to being hit, punched, poked, flicked, twisted, diddled, or dorked with, had a natural deactivated state to begin with. All schematics, all the time, are always drawn in their deactivated state, a point I will come back again and again to belabor in the hydraulics, electrical control of hydraulics, and motor controls playlist. For now, you must simply understand and differentiate between the two mutually exclusive states of deactivated and activated. People use all sorts of weird terms for these two states. However, in an effort to establish some clarity and consistency, I will always refer to them as deactivated and activated. Switches, by being actuated, can transition from their deactivated state to their activated state, and vice versa. An electrical load, in contrast, is something that can be de-energized or energized. An electrical load might be a lamp, a motor, a coil, a buzzer, or anything that draws current and is put to some recognizable use. A de-energized electrical load experiences no current flow through it. An energized electrical load experiences current flow through it. Please do not use the terms unperturbed or perturbed as is common in some countries when describing switches and electrical loads. Nor should you apply the terms commonly reserved for switches to loads, nor apply those terms commonly reserved for loads to switches. It perturbs me to no end. Stick with the terms I'm using, we'll get along just fine. Again, I'm looking to establish clarity and consistency. Switches are named and drawn in schematics using their natural deactivated state. This brings with it an important distinction. A switch, when it is in its natural deactivated state, can be in one of two normal positions. It could be normally open or normally closed. A normally open switch in its deactivated state, as the name implies, is open. This is its natural deactivated state. When actuated, it transitions to its activated state, that being the opposite of deactivated. A normally open switch, when actuated, closes. It makes sense. A normally open switch is normally open when you're not poking it. When you poke it, it closes. In contrast, consider a normally closed switch. A normally closed switch in its deactivated state, as the name implies, is closed. This is its natural deactivated state. When actuated, it transitions to its activated state, that being the opposite of deactivated. A normally closed switch, when actuated, opens. It makes sense. A normally closed switch is normally closed when you're not poking it. When you poke it, it opens. Put this understanding to a test. What is the resistance of a normally open, often abbreviated NO, switch when it is deactivated? In its deactivated state, it should ideally present infinite resistance because it's open. What's the resistance of an NO switch when it's activated? In its activated state, it should ideally present 0 ohms of resistance because it's closed. Consider application of a normally open switch in an electrical circuit. When it is in its natural deactivated state, the electrical load is de-energized and it experiences no current draw. When an operator actuates the switch, the normally open switch transitions to its opposite activated state and closes. The electrical load is energized and experiences current draw. A normally open switch employed in this fashion might be labeled on or start. Consider the entirely opposite scenario. What is the resistance of a normally closed, often abbreviated NC switch, when it is deactivated? In its deactivated state, it should ideally present 0 ohms of resistance because it's closed. What is the resistance of a normally closed switch when it is activated? In its activated state, it should present ideally infinite resistance because it's been opened. Consider application of a normally closed switch in an electrical circuit. When it is in its natural deactivated state, the electrical load is energized and experiences current draw. When an operator actuates the switch, the normally closed switch transitions to its opposite activated state and opens. When it is in its activated state, the electrical load is de-energized and does not experience current draw. Totally opposite of our earlier application of the normally open switch. A normally closed switch employed in this fashion might be labeled stop or off. Notice I've been using a slightly different schematic than the single-pole, single-throw switch we've previously employed. The single-pole, single-throw switch I previously used was something known as a single-break switch, and that there is a single point where the single pole breaks or makes contact with its single throw. The normally open and normally closed switch I'm using here are still single-pole, single-throw switches because there is one moving contact and one position it can be placed in. However, they're both known as double-break switches because there is now 2 points where the single pole breaks or makes contact with its single throw. A switch with double breaks provides greater volume of contact material, permitting greater heat dissipation, longer switch life, and greater breaking capacity. Finally, consider 2 single-pole, single-throw switches integrated into a single device, one being a normally closed switch from terminals 1 to 2, the other being a normally open switch from terminals 3 to 4. Switches are often paired together in packages with a mechanical interlock between the 2 switches. The mechanical interlock is the dashed line. Terminals 1 and 2 are electrically isolated from terminals 3 and 4. However, when an operator actuates the single button on the outside of the package, the normally closed side opens and the normally open side closes. Understand this switch package is a little different than the double pole, double throw switch we discussed earlier, because for this package, when one switch opens, the other closes. I feel like I'm opening a barrel after barrel of rage-infected monkeys here by introducing tricky definition after tricky definition. But for now, just think of this as 2 electrically isolated, yet mechanically interlocked switches, both with double break contacts. This is often called a break-make push button because when you actuate the switch, the top switch opens and the bottom switch closes. Such a switch package might be employed to our advantage by turning off or preventing one electrical load from being energized when another is being turned on. For example, you would never try to simultaneously spin a motor clockwise and counterclockwise at the same time. Not only will it destroy the motor, it flat out doesn't make sense. And a mechanically interlocked package of a normally closed and normally open switch can be employed, as we'll learn in later lectures on motor controls, to prevent some dummy from doing so. Finally, let's discuss activation period and differentiate between momentary and maintained contact. Maintained contact switches stay in one state until actuated into a new one, and then remain in that state until actuated once again. This is like a light switch in your house. When the lights are off, you hit the switch and the lights come on. When you take your finger off the switch, the lights stay on because the switch maintains the closed state until you hit the switch again, which returns it to its open state. Think of how hard it would be to get anything done in your house at night if you had to keep your finger on the switch the whole time to keep the lights on. In contrast, a momentary switch only remains activated when it's being actuated. If a momentary switch isn't being actuated, they remain in their deactivated state. An example of a momentary switch might be a spring-loaded button that enters its activated state the moment you press it and instantly returns to its deactivated state the moment you stop pressing it. The keys on your keyboard are momentary switches. Let's take a look at a couple switches with our DMM and ohm meter mode and see if we can apply the terms normally open, normally closed, and momentary versus maintained to their constructional and electrical characteristics. Here's an emergency stop button. It's a big old red mushroom-shaped actuator that is conspicuous and easily actuated. This particular switch has 4 terminals. One pair of terminals being a normally closed switch from 1 to 2, and the other pair of terminals being a normally open switch from terminals 3 to 4. The schematic indicates there is a mechanical interlock between the 2 switches acted upon by the mushroom button. Start thinking now what an ohm meter might read from terminal 1 to 2 and from terminal 3 to 4 in both this switch's deactivated and activated state. In its deactivated state, i.e. the button has not been actuated, the ohm meter indicates a connection from 1 to 2. This is the normally closed switch. When the button is actuated, the ohm meter indicates an open from 1 to 2. It makes sense. The normally closed switch opens up when you actuate it. Here's an important point. When I release my hand from the mushroom button, the ohm meter indicates there is still an open between terminals 1 and 2. This switch is maintaining the active state of open. It makes sense. That's what you typically want an emergency switch to do. If you press it once because you're in a dangerous situation, you'd like that dangerous situation to not only stop after you've hit the button, but also stay stopped. This particular switch from 1 to 2 is a normally closed switch in its deactivated state. In its activated state, it becomes an open. Additionally, this is a maintained switch. Only when I reset this emergency switch into its deactivated state does the ohm meter indicate there is now connection between 1 and 2 and it has returned to its normally closed state. This is what the dashed line modifier in the schematic means. The top portion is the mechanical interlock between the normally closed and normally open switches. This bottom portion is the maintained contact portion and indicates that it must be reset. A quick note on emergency stop buttons. Resetting an emergency stop isn't as simple as pulling the mushroom button back out. Normally they need to be rotated a half turn for it to reset. Sometimes the face of the button has an arrow to remind you of this necessity, sometimes it doesn't. Additionally, some emergency stop buttons have a green ring on the stalk of the mushroom button to indicate that the switch is in its deactivated or go state. Look at emergency stops from the side to make sure you see the green band before you return equipment to service. Because they're placed in easily accessible locations for quick access in emergencies, the same convenient location means they're easy to accidentally bump. Sometimes emergency stops in high traffic areas employ guards that allow the button to be actuated in an emergency but prevent it from being bumped by a cart or your backside. The other set of terminals 3 and 4 on this same switch do almost the same thing in reverse. In its deactivated state, the ohm meter indicates no connection between the terminals of this normally open switch as can be expected. When the button is actuated, the ohm meter indicates closure between 3 and 4. It makes sense. The normally open switch closes when you actuate it. Again, when I release my hand from the mushroom button, the ohm meter indicates there is still closure between terminals 3 and 4. The switch is maintaining the active state of closure. Only when the button has been reset to its deactivated state does the ohm meter indicate an open between 3 and 4. This particular switch from 3 to 4 is normally open switch in its deactivated state. It is a closed switch in its activated state. Additionally, this is a maintained switch. You'd think this wouldn't be a particularly useful set of terminals in an emergency stop switch. However, realize this extra set of terminals can be used to communicate to other machines or other parts of the same machine that this particular emergency stop button has been hit. As we'll see in later lectures, operations of immense complexity can be controlled by simple switches. Here's a push button. It's a sickly mustard-colored, slightly extended button actuator. Push buttons come in all colors, including illuminated varieties, and sometimes with flush, half-shrouded, or slightly recessed buttons. This particular switch has 4 terminals, almost identical to our last emergency stop switch package. One pair of terminals being a normally closed switch from 1 to 2, and the other pair of terminals being a normally open switch from terminals 3 to 4. The schematic indicates there is a mechanical interlock between the two switches acted upon by the push button. Start thinking now what an ohm meter might read from terminals 1 to 2 and from terminals 3 to 4 in both this switch's deactivated and activated state. In its deactivated state, i.e. the button has not been actuated, the ohm meter indicates connection from 1 to 2. This is the normally closed switch. When the button is actuated, the ohm meter indicates an open from 1 to 2. It makes sense. A normally closed switch opens up when you actuate it. This switch is behaving exactly like the first switch on the emergency stop button, but with one important distinction. When I release my thumb from the button, the ohm meter indicates the spring-loaded push button has returned to its deactivated state of closed. This is a momentary switch. Only when I actuate it will these switches be in their activated state. This particular switch from 1 to 2 is a normally closed switch in its deactivated state. It is an open switch in its activated state. Additionally, this is a momentary switch. The other set of terminals 3 and 4 on this same switch do almost the same thing in reverse. In its deactivated state, the ohm meter indicates no connection between the terminals of this normally open switch, as can be expected. When the button is actuated, the ohm meter indicates closure between 3 and 4. It makes sense. The normally open switch closes when you actuate it. Again, when I release my thumb from the push button, the ohm meter indicates the spring-loaded push button has returned to its deactivated state of open. This is a momentary switch. Only when I actuate it will these switches be in their activated state. This particular switch from 3 to 4 is a normally open switch in its deactivated state. It closes in its activated state. Additionally, this is a momentary switch. If I wanted to add a third switch to this same package, actuated by the same push button, one can use something called an auxiliary. Notice the green plastic plunger. This is the mechanical interlock mechanism used by the push button on the front to activate this additional set of contacts while maintaining electrical isolation. This particular auxiliary simply screws onto the back of the switch package and the plastic plunger slips into a well. This additional switch could again be used to control a complex system. Lest you think all switches are manually actuated, let's close up this lecture with a quick look at a limit switch, an automatically actuated switch. The first thing you'll notice about the limit switch is the long arm. Basically, if something bumps into this arm, the limit switch will be actuated. This could be used to limit, hence the name, the linear or rotational travel of a physical object. For example, modern industrial wind turbines typically feature limit switches inside the blades that indicate a blade has been pitched either to the 0 degree or 90 degree position. As the blade is being rotated into position, a metal tag strikes the limit switch. If the tag is misplaced or the limit switch arm broken off, the controller doesn't think the blade has reached its limit. Ask me how I know this. Actually, don't. This lecture is getting long enough already, and I don't want to make it any longer by including technically relevant and entertaining stories. When we crack open the limit switch, we're presented with two noticeable differences between this and the previously inspected emergency stop and push button packages. One, tiny Lilliputian wires. This limit switch is obviously rated for lower current and voltage than our previous devices. This is awesome and totally makes sense. A limit switch is a sensory device only. Why should it carry high current or use high voltage? For that matter, why would a push button? As we'll learn in later lectures, the control aspect of a system, being that aspect of a system that senses inputs, makes decisions, and delivers commands, is often run on safer inputs, i.e. lower voltage, than the power aspect of a system, being that portion of a system that lifts, pumps, crushes, turns, grinds, or saws. The control aspect is the brains. The power aspect is the muscle. 2. You'll notice it's using subtly different schematics and terminal numbering. Don't worry about the rationale behind the terminal numbering for now. I'll explain this later. This is also an integrated package of two switches. The lower switch is between terminal 1-1 and 1-2. The upper switch is between terminals 2-3 and 2-4. I want you to take a guess at what the schematic means. This limit switch is using IEC schematics. If IEC isn't your thing, you can always look it up on the internet, or just kind of guess what the schematic is saying. There is a vertical bar between the lower and upper switch. My guess is that this is the mechanical interlock. When the actuator arm is tilted, This should actuate both switches from their deactivated state to their activated state. The bottom switch is a vertical connection between its pole and throw. The top switch is missing this modifier. My guess is that the bottom switch is the one that's normally closed in its deactivated state. The top switch, since it's missing this modifier, is probably the one that's normally open in its deactivated state. Let's stop guessing. Even if the schematic wasn't available or written in Martian in invisible ink, you should be able to still figure out how the switch works using an ohm meter. Come to think of it, this might be a good practical skills test. Hint, hint. In its deactivated state, i.e. the arm isn't being tilted or torqued by anything, the ohm meter indicates a connection from 1-1 to 1-2. This is a normally closed switch as we anticipated. When the arm is torqued to one side, the switch is actuated and the ohm meter indicates an open from 1-1 to 1-2. It makes sense. A normally closed switch opens up when you actuate it. When the arm is brought back to the center, the ohm meter indicates connection from 1-1 to 1-2. This is a momentary switch because it has returned to its deactivated state of normally closed. What is interesting to note about this particular limit switch is that it can also be actuated from the other side. When I torque the arm in the other direction, the ohm meter indicates an open from 1-1 to 1-2, meaning the normally closed switch has been actuated into its active state of open. Again, when the arm is returned to the center, the ohm meter indicates the switch is returned to its deactivated closed state, supporting our earlier observation of this being a momentary switch. Finally, the ohm meter indicates the same song in reverse for the 2-3 and 2-4 terminal pair. When in its natural deactivated state, the ohm meter indicates no connection. This is a normally open switch. When actuated, the ohm meter indicates a connection, meaning the switch has closed. When returned to the center, the switch returns to its deactivated open state. This whole switch package is a limit switch that is automatically actuated via its arm. It has two electrically isolated switches mechanically interlocked together. One switch is a normally closed switch from 1-1 to 1-2, the other being a normally open switch from 2-3 to 2-4. Both switches are momentary. This concludes the introductory switches lecture. Believe me, we have not seen the last of these devices. I've yet to discuss relays and contactors at any depth, and I've purposely left out a slew of fascinating facts that would only be received as noise. This lecture, the first time through, might have seemed like you were drinking from a fire hose, but the advantage of this format is that you can always revisit and rewind to the parts you're struggling with. For now, you should be able to differentiate between high side and low side switching, identify the number of pulls and throws for a switch, determine if a switch is manually or automatically actuated, determine the deactivated state of a normally open or a normally closed switch. You should be able to determine the activated or opposite state of a normally open or a normally closed switch, determine if a switch is momentary or maintained, and finally, you should be able to determine the effects of open and closed switches and open and short circuits in basic series circuits. If that's too much to ask, here's this. If you graduate your basic electronics class with this simple understanding, I will consider my time having not been spent in vain. Voltage is across. Current is through. Open switches will not allow current to flow through them. Opens will have a voltage drop across them. Closed switches will allow current through them. Ideal closed switches will have no voltage drop across them. This simple cheat sheet is helpful beyond measure when designing, installing, maintaining, troubleshooting, and modifying electrical systems. If nothing else, remember this. In conclusion, this lecture took a close look at switches and restricted their analysis in the open and closed position to series circuits. We discussed shorts and opens in series circuits. We learned a switch can selectively energize or de-energize electrical loads in series with a switch. We compared and contrasted high side and low side switching. We applied the terms open, closed, make, break, pull, throw, manually actuated, automatically actuated, deactivated, activated, energized, de-energized, normally open, normally closed, electrical isolation, momentary, maintained, and mechanical interlock to an introductory discussion of switches. Finally, we briefly discussed the switches in series logical AND operator and the switches in parallel logical OR operator. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.